Hello, my name is Aaron. I'll be filling in for Jacob in today's lab video, which will be covering Lab 5, Transistors 1, the BJT DC Behavior, and Curve Tracer. We'll be introducing this new item, the bipolar junction transistor, that's the BJT. And it's a 3-terminal semiconductor device. When looking at the flat end of the pin, we can look at the left side and we'll see that this side is our emitter pin. The middle pin is generally the base, while the rightmost pin will be your collector. And again, this is looking at the flat side first, flipping it over, and then reading it from left to right. If you're unsure of where your E, B, and C pins will be, then you can refer to the data sheet. Be sure that you're looking at the data sheet for your correct item, and the item we'll be using in this lab is the 9014L BJT. There's 2 different types of BJTs. We can have a NPN, which is just a negative, positive, negative setup, and then we can have a PNP, which is just a positive, negative, positive setup. You'll see here that the arrow will denote the emitter. When using the BJT into your system, it'll have 3 different modes that it can run at. It has a saturation mode, which it acts like a switch, a closed switch when it's in this mode. You have the Q point or active region, and this is when the collector, is in reverse bias mode, while the emitter is in forward bias. The last mode that it can operate in is this cutoff region, or this cutoff mode. This is when the emitter and the collector are both in forward bias mode. So this results in no flow of current. In today's lab, our main goal in part A is to observe this here, these curves on the oscilloscope. So we'll be dealing mainly in the active region in part A. In part B, we'll be using an application that the BJTs have, which is with either a high or a low load resistance. We can then amplify currents or decrease currents that are given to it. Our example that we'll be using for part B will be the current mirror setup, which uses 2 BJTs of the same type, which in our case, we're going to be using the same NPN transistor as we used in part A. We'll be manipulating the current by giving a high load resistance, which will provide a low current, while a low load resistance will provide a high current. For part A, we'll be using this schematic where we have a varying resistor, our 9014L BJT, a 10 volt peak to peak provided from our function generator, a varying voltage, and then a resistor of 10 ohms. The actual measurement measured with the digital multimeter for this resistor came to 10.5 ohms. This varying voltage is provided from the power supply. Once we've constructed our circuit, we're then needing to obtain this curve. Once we've determined our variables, which in my case, I have the power supply voltage being 5 volts and the varied resistor starting at 0.463 mega ohms. Now that we're satisfied with our first curve, we can disconnect our red lead from the power supply. This flattens our curve, as you just saw. And we're gonna increase our voltage up by 2 volts. This will change the current, and this will also change the look of the curve. It will raise the curve to a new level. And we want to keep doing this to identify each new level. And we'll increase it again. And we'll increase it again. We'll increase it again. And then we'll increase it one more time. And so as you see, as we increased our voltage, we increased the height of our curve, where these curves that we were seeing represent the Q point, or the active point. And this is the schematic for part B, where we'll have R5 actually measuring out to 91.6 kilo ohms. R4 that will vary from the breadboard. R3 is actually 99.3 ohms. R2 is 982 ohms, and R1 is 995 ohms. The two BJTs, these will be the same as before in part A. And we'll have 5 volts coming from the DC power supply, and we'll have -5 volts coming from the signal generator. Once the schematic has been made, we're then asked to measure the voltage that travels across R5. And when we measure the voltage traveling across R5, you'll see that it's 9.31 volts. And we can use this to find our reference current by using Ohm's law, where V equals IR. And R is the measured resistance that I mentioned earlier. Next, it's asking us to measure the voltage across R4, and to do that, and we'll have that the voltage across R4 is -44.6 millivolts. Once we have that, we can use that as our first marker, and then we can begin varying R4 and measure everything as we did before, so that we can get a V sub 4, an I sub out, and then we can compare the I sub out and the I reference and gather a percent difference. I will be calling out different resistances and different voltages that we'll use. We'll scale from 5 to 10,000 kilo ohm, 10 kilo ohms. When R4 is 1.072 kilo ohms, we get that V4 will be -102.1 millivolts. When 1.548 kilo ohms is applied, we have V4 being -148.1 millivolts. At 2.011 kilo ohms, we have -191.2 millivolts. At 2.501 kilo ohms, we have -237.9 millivolts. At 3.080 kilo ohms, we have -294 millivolts. At 3.584 kilo ohms, we have -341.9 millivolts. At 4.05 kilo ohms, we have -385.6 millivolts. At 4.51 kilo ohms, we have -2.49 volts. At 5.03 kilo ohms, we have, looks like it's jumping around a whole lot. -0.479 volts. At 5.61 kilo ohms, we have -0.533 volts. At 6.01 kilo ohms, we have -0.568 volts. At 6.63 kilo ohms, we have -0.629 volts. At 7.1 kilo ohms, we have -0.674 volts. At 7.62 kilo ohms, we have -0.722 volts. At 8.09 kilo ohms, we have negative 0.768 volts. At 8.54 kilo ohms, we have negative 0.810 volts. At 9.08 volts, we have negative 0.860 volts. At 9.55 kilo ohms, we have negative 0.904 volts. And then finally, at 10.12 kilo ohms, we have negative 0.960.